Well, why don't I go ahead and get rolling here. Today we're going to be, I guess, sort of talking about more the tools than the concepts. Let me go ahead and fire this up a little bit, make this full screen. We're going to be talking about the tools, or doing the plumbing, or whatever you want to say here, basically talking a lot about how to do some of this stuff. Particularly, you may recall from our last session, as well as from what you may have already attempted hands-on, is that working with the WinBUGS GUI can be tedious to some degree. In addition, I think one of the bigger disadvantages when you're trying to work in a production mode and you want to have mechanisms for being able to check the quality of your work and things like that, the GUI doesn't give you any easy ways of saving the steps that you take as you're doing the work, and without being able to record that, it's difficult to be sure of exactly how you generated your results. We'll be talking about some methods that allow you to both to some degree automate the process of working with WinBUGS, and at the same time you can sort of end up with sort of a self-documenting script that captures all the steps that you're working through. So let's go ahead and start talking about that. Let's start with sort of the first step on the way to that, and that's the fact that WinBUGS 1.4, unlike some of its earlier versions, has a scripting language embedded within it, and it's that which we're going to be taking advantage of both when we use it directly as well as when we work from R for doing a lot of our work. So let's talk a little bit about the bug scripting language. So first of all, it does permit batch mode operation, and you can launch a bugs run using the bug script from any program that's capable of running DOS commands, R being the example we're going to be working with. Let's see, somebody's saying audio is cutting out. Joe, any confirmation from your end on that? He says it sounds fine there. I guess Mike, does it still seem to be cutting out right now? Let's see. Got some goods, and I don't know, Mike, if you're having any trouble, you might want to check at your end in this instance, because it sounds like it's working for others right now. Okay, so let me continue on here then. So one of the things you can do if you write a script, you can either run it from within the BUGS GUI, or you can use it, or it can be something you can specify in the command line, where you can run a DOS command that launches WinBUGS and uses the script. You can write an R script that would create your WinBUGS data sets and your initial estimates. It would run WinBUGS and then analyze the bugs generated samples that come out of that. And in fact, that's what we'll be leading towards in terms of let's see. Okay, yeah, Mike, I'll just comment there. It looks like it's probably at your end, because so far everybody else is indicating the sound's okay. Let's see. So we'll be working with R scripts in that fashion that take advantage of this scripting. And I was just commented here, you can take that to further extremes. For instance, you can write an R script that simulates a bunch of clinical trials and analyzes each one using WinBUGS. So let's see, I think I want to jump right to Windows World. Let me check. Well, no, here, let's see. Well, rather than doing it from here, I've got a slide you can see here that is that's showing the a WinBUGS script, but I think it's better if we actually do that right from WinBUGS. So let me go ahead and okay, we're supposed to jump to Windows World. Let's try that again. There we go. Oh, you know what? Okay, is that Windows World? No, that's not Windows World. Where the heck am I? Excuse me while I figure out what I'm doing here. Ah, I see what I did. Excuse me while I straighten this out. That wasn't supposed to be in that window. Move that up there, and now we'll get into Windows World. So why don't I go ahead and step through the process then of working through this on a from Windows. And first of all, let's take a look at a bug script right from within WinBUGS. So let me go ahead and launch WinBUGS here. There we go. And if you go down into the MI250 folder, and then go down to the linear folder within that, if you look inside, you see various things that we've actually worked with before in a previous demo. But in particular, what I want to grab here, there's a file there that's just called script.odc. Let me go ahead and just drag that over here. Okay, and we've got a script with several script commands that are in here, which are maybe not, they're probably too terse to be entirely self-descriptive here. So let's give you some more information. Let's go to the user manual. Let's open that up. Actually, why don't we make Bugs full screen here? Okay, and let me scroll down here. Okay, you'll find in the contents it refers to batch mode scripts. Let's go ahead and go into that. Okay. Let's see, unfortunately I'm not sure I can do it. Let me see if it'll let me enlarge this here, but I'm not sure that it will. I'll take a shot. It may mess up the formatting quite a bit, but let's see. Let's try 16 point. And it's ignoring me, so I think we're kind of stuck with it. So this may, I don't know if this is looking a little small on your screen. You might want to go ahead and open up Bugs yourself and take a look at it on your own screen. Oops. Okay. So it spends a little time here talking about the scripting language, and I encourage you to go ahead and read through that. But the key thing I wanted to show you here is that you have essentially a lookup table on the bottom here, where on the left-hand side it shows the script command and the syntax for that, and on the right-hand side it shows you the menu equivalent to that. So for example, when we're working with a model, and so normally we would, so if we had a model open, in fact, let me open a model. Okay, for some reason Windows is being slow to respond here. Come on. Okay. Come on. Ah, it escaped. Okay, if it's going to be stubborn, let's shrink that and try again. Okay, let's go ahead and bring. Why don't we go ahead and bring the one we used for an example last time, that linear1.odc model. Okay, that's if Windows decides to respond to me. Or not. Let's try that again. Here we go. Oh, I just realized what it's probably trying to do here. It's probably trying to stuff that into the document when I'm dragging here. Oh, no, I think we're okay. Okay, so recall we had the model before. So if we wanted to compile this model, for instance, we had to first go to the model menu. Okay, model menu, come on. Okay, and I would select specification, would open that up. So what I would have to do is I would highlight model over here and click on check model, for example. Well, how would I do that from the script? Well, if we go back to our script description here, okay, that shows up right here where you can see where it has model specification check model here, corresponding to that sequence of things that we did using the menus. Well, the equivalent to that is the check command, where in parentheses you put the name of a file, and in fact that would generally have to be the whole path name to a particular file. So you would put that in there. So for example, if we go back to our script that I brought up, okay, you can see that, well, the first step that was in here, it says display log. All that's going to do is bring up a window inside WinBUGS that shows, well, it's a log showing a log of the various commands and responses that it's going to have. So it displays it. If you don't put that there, all of these things will happen, but you won't actually see the results on screen. So the statement I was just talking about is right here, for example, where I have check, and then I have the whole path to the same model we were just looking at, the linear 1 ODC. Because I'm working from my C drive. If you look here, I'm working from my C drive. That's where I've got it. If you do this from your USB stick, you'd have to put the appropriate drive letter right there for whatever drive got assigned to your USB drive that you're working with. But otherwise, I think this should be correct. By the way, I'll make a comment here. In the stuff I sent you in the USB, your script.odc files has somewhat different path names. I think there's something like I forget what was it exactly, but it was E and something like, WinBUGS course or something like that, or maybe it was Metrum Bayes course or something like that for that instead of MI250. So with your current path names that you're working with, you'd have to change it to something that looks a bit more like the one I've got right here for it to work. Excuse me. So we do that. Now recall the next step we would have to do if we're working with our model. I open this up bigger again and pull our model up. Okay. There's linear 1. Now the next thing we would have done is we would have gone down on the model file I had here, and we've got the data right within the same file, and I would have selected list here and clicked on load data. Well, we'll have to do something similar but slightly different when we're working with the script. Let me bring up our table again. Now for data, you can see it actually uses a script command name, which is called data, and then you put the name of a file that contains your data. Now when you're working with scripts, you can't do like I did before, where you had everything in one file, where I had the model, the data, and the initial estimates in one file. Instead, you need to separate them. Now it turned out when I used the check model, it'll actually work okay with this model file. It'll just ignore the data and the initial estimates that are down below. But if I tried to use this same file as my data source, it wouldn't work. I need something a little cleaner, so I actually have to create another file, and I've done that. So for example, I've got a, okay, what happened to my data? Okay, let me fix that. I believe in yours you would have your data here. I think I made a mistake when I probably got carried away deleting something at one point here, but I can fix that. Okay, let me grab the data. Just going to copy these over. I believe you have these on your drive. Okay. Let me go back to here. Okay, there we go. Okay, so I needed to create a separate data file. So for example, if I take a look at data.txt right here, just pull that up here. Come on. Apologies for the slow response here. I'm not sure why Windows is being painfully slow. I don't have all that much going on with it at the moment. Okay. Okay, there we go. There's my data set here. Let's see, the formatting looks a little funny only because it's doing some wrapping here because of the large font size here, but recall this is actually identical pretty much to what we have right here on the right hand side under the linear 1, except it's formatted just slightly different. But you can see it's a list with a vector here called x and another vector here called y, so it's the same except for the funny notation here. It's since it's got scientific notation on it with way too many significant figures in it. But that's the data file we're going to be working with in this. And to do that, all you do is give the command data, and you can see that inside of our script right here. So that takes care of that. Well, and then recall the next step, if we were doing this from the GUI, would be to compile. And that's also the next step inside here. And compile, the command is one, it's just compile, and the only argument there is the number of chains that you're going to want to run. So I went ahead with 3. And then if I've got 3 chains, I'm going to want to read in 3 initial sets of initial estimates. And the initial estimates code, pull that guy up here, come on. There we go. Okay, in a minute I'm going to go and see if I've got something else running on this computer I don't know about, because it's awfully slow. Okay, this is getting ridiculous. Excuse me. Okay, let me close down a few windows here in the hopes that that will make things a little bit better here. Believe it or not, I'm doing things you can't see here in hopes that maybe if I shut a few things down, things will speed up. Okay. Okay, let's see, I don't need that at all. I have a feeling I may have found the culprit here. Let's see. Okay, let's see if things are moving a little speedier now. One can only hope. Well, that doesn't seem to be. I think I may relaunch Windows here in a moment. Sorry for the delays on this. Hey Joe, have you ever had web meeting do this to one of these computers before? Trying to decide if that's the culprit or whether it's parallels. Either way, it's frustrating. Well, Joe says first time he's seen something like that. Okay, come on. Frustrating part here, of course, it's difficult to do this without having a functional Windows thing going on here. Doubly frustrated since I did a little practice session before class to make sure everything was working okay. Okay, we finally got that part to close. Let's get a little bit of the flotsam off it. We'll take one more shot with this before I go through the trouble of actually relaunching Windows, because that also takes a while. But that may be necessary from the looks of things. Okay. This has gotten beyond the pale here. Well, while this is happening, let me talk about one thing while I'm trying to get this straight here. Next week, I will actually not be able to do the course live. My current plan, hopefully that will work out, is to will be to pre-record the course or record the lectures for next week. I'll let you know as soon as I can when those are up, or if for some reason I'm not able to do that. If all else fails, we do have one extra week built into the schedule for makeup. Okay. This is one of those times, yeah, right now Windows is completely not responsive. There we go. Well, it's hopefully going to finally let me interact with it in a minute. Let me go at least tell you what the components are. I can go ahead and use this slide for the moment here to that's only if anything's going to work with me. Okay. Okay, the steps I was going to be taking through in here, and hopefully we can get back to that on the real system, but you go through, you do the check, you bring in the data, you compile it just as before. Then to do the initial estimates, if I'm going to have more than one chain, I need to give initial estimates for each one. Now in theory, all of them could be the same, but that doesn't really provide you with the kind of convergence diagnostics you'd like. So ideally you would create 3 initial estimates files that are somewhat different from each other, and then you would read them in one at a time using the inits command, and the first argument for that is which chain that corresponds to, and in our case that would have to be 1, 2, or 3, and then you give the file name. Then if there's any uninitialized random variables in there, you do the gen.inits command, and that one doesn't have any arguments, but you still have to provide the open and close parentheses there. And now if you're not sure whether or not you need to generate additional estimates, go ahead and put it in there. The worst that'll happen is it'll just tell you it doesn't need it. So generally I would by default include that in there. Then you have to tell it things like which parameters do you actually want to monitor. So you go ahead and put those parameters in there. And you use the set command for doing that, and then the name of the corresponding variable. Then update is pretty much what it sounds like. You run a set of MCMC iterations, and the argument for that is the number of iterations you want to do. So what I've just gone through here is a very simple sort of script here that does all the steps that we would have done had we done the GUI. The next component here, the coda command, will save. Now, by the way, the first argument for coda is going to be also the chain, but if you put a star, it'll say, okay, you want to do this for all of the chains. And what coda will do is it'll write out a set of files. It's going to write out the MCMC iterations for each one of the chains, and it'll create a separate file for each one, plus another file. So in this case it would be a 4th file, which will be sort of an index to where the different variables are stored within those different files. Then you can do various things, like when we were doing plots before and some tables. Stats will do some statistics, summary statistics on the MCMC samples for the various parameters that you specify. Density will create these marginal density plots, and the history will create history plots. AutoC creates the autocorrelation plots, which I think I showed you briefly during the last session. And then finally, if you'd like to save the log which shows the plots and the results of doing the commands, you just say save, and you give a path to save the log file in. And then if you don't want the GUI to stay open, then you just put a quit command in there. Okay, let's go down here and see if what's going on with Windows here. Okay, why is it pointing at Z? I have no idea. Okay, let's see if it's being responsive or if I need to completely restart it. It's not super speedy, but it seems to be moderately responsive here. Let's see. That's not so moderately responsive. Okay. That's way too slow. Okay, we are going to be putting this out of its misery, I think, here. That's not acceptable. Okay, there we go. Anyway, what I'm going to do here is see if I can just sort of restart up Windows here. Okay. While it's doing that, let's talk a little bit about some of the things we're going to be doing with R. Is that thing actually shutting down? I'm not sure it is. I didn't really have a plan B here for the course for today, so hopefully we can get this going. Okay, what's it doing there? Okay, well, it's doing whatever annoying thing it's doing here. Let's talk a little more about where I'm going to be trying to take this. Okay, what I was going to be leading to next is something a little more powerful than just working with the scripts by themselves. So you could actually do a fair amount with just the scripts, but you still are going to need tools for doing things like data management and generally the kinds of plots and tables that you get directly out of BUGS are, let's just call them less than optimal. So we'd like to have some other tools, and we're going to use R to pull these things together. So let me start by mentioning some tools that are kind of specifically built around WinBUGS. One is there's a package called R2WinBUGS, which is an R package of functions that allow you to run WinBUGS. I say or OpenBUGS. I probably should have deleted that actually, because the current version of R2WinBUGS is not currently functioning with OpenBUGS, and they're actually about to release a new package called R2OpenBUGS. So let's just say it's got packages of functions for running WinBUGS. In addition, there's a package called Coda, which is mainly for analyzing the MCMC results once you've generated them. It's got some code in there for instance, for grabbing those Coda files and bringing them into R, and then doing things like history plots and various other kinds of post-processing with the MCMC results that come out of BUGS. And then finally, I put together a small number of, as I call them, handy-dandy functions that I provided that are for manipulating and plotting MCMC results. Much of these actually take advantage of the Coda library in conjunction with some of the plotting routines that are available within R. And the idea is to go through an R demo. So let's see if we can bring this. Oh, for crying out loud, yes, I want you to turn off. Because what we'll do here, if I can get this thing functioning correctly here, is we'll go through a demo of some of the tools here that are available in R and walk through that process. So in fact, what I'll do is just take the linear regression example that we've done and illustrate how would we do that if we had a set of R tools to aid with the process for doing things like preparing files that contain data and initial estimates, to run WinBUGS, and to analyze and plot the MCMC results, and then finally to save it all in a specified directory so that you've got a record of the results as well as how you got them. And for our example, that's all going to be done using an R script that's in your USB drive called linear1b.r. Okay, let's see if Windows is gone. Yes, I want you to end the program. Don't mind me, I talk to computers way too much. Okay, well, it's actually doing that. Why don't I go ahead and pull it up in where we can see it here. Okay, why did it switch? I didn't want it to do where it just headed there. Let's see. Let me bring up the file in something where we can look at it. Okay, take a second here. I'm just opening up the that linear1b.r file so we can take a look at that. I'll just, for the time being, I'll just bring it up in a text editor here on the Mac. Okay, where are you? Okay, let me. Oh, sounds like Windows was just shutting down. No, it's still monkeying around with it. Okay, let me see about making this a little bigger. Okay, hopefully that's a little easier to see. Probably do a few strange, oops. Probably do a few strange wraps here because of making it that bigger, but hopefully you can see most of it. So let me, what I wanted to do is run it first so that you can see what it looks like after it runs, but we'll have to wait until Windows comes alive again. So let me sort of point up the pieces. So this is now going to be an R script that we're going to be using for running WinBUGs. Actually, why don't I go ahead and pull up the rest of the stuff that we're going to look at as part of it here. Okay, so we've got one of the first things that happens in here is basically a lot of bookkeeping that's going on top here to set it up. I specify a model name, and the conventions I'm going to use here is I'm going to use that as the root name for a number of files. In particular, it's the root name for the model file. So if we go in here, you'll see there's where'd it go here? Yeah, there is a file in here called linear1b.txt. In fact, let me enlarge. Maybe I can enlarge this for you too, so you can see it maybe a little better. Okay, so I'm going to use this linear1b.txt, and that actually contains the same linear file, the same linear algebra file or linear regression file that we used before, but now it's going to be in the text format. Okay. So you can see this is now just the model. It doesn't have any of the other components in here, the data or the initial estimates, but otherwise I believe this is identical to what you've seen before. So that's the model file that we're going to be working with. But also it's going to use the same name to write out the results. It'll use that consistently through here. Here I've defined the directory that it sits in, and which is just named linear, so that's just the name of the directory. So I call it example dir. And then the rest of this whole mess right down here is again pretty much just bookkeeping, where I do things to get the appropriate home drive here. So what all this nonsense is doing is it says, okay, which version of R are you using and which directory does it sit on, because the way I set up your USB drives, the R and everything else is on the same drive. So this will just pick off, all it's doing is picking off the drive letter in that one. Then I define a directory for the entire course. So you set that to whatever is appropriate, but by assuming you haven't changed your setup, it should pick it off appropriately. So you shouldn't have to change that. Similarly, the example directory is just that plus linear stuck on the end of it with the file path function here. The tools dir is where a few different tools exist. In particular, if you look inside your USB drive, there will be, actually let me put this alphabetical, there'll be a directory called bugs tools, and inside of it there's a couple of files. They're just R scripts containing some function definitions here. So you'll see one called BUGSModelLibrary, which are just a few miscellaneous functions I occasionally draw on in these scripts, and then there's BUGSTools.R, which has functions that I use within all of the scripts that we'll be doing. Here's where it's going. Let's see if I can refire this thing here. Actually, let me knock off parallels entirely and restart it. Assuming it's going to. There it goes. Okay, that'll interrupt us every now and then. So there, and we'll look at those in a little bit when we get to the context where we actually use some of those. Then I tell it, okay, where it does. Okay, excuse me while it jumps there. Okay, I know it's going to ask me one more thing here before I jump back. Okay, hopefully that'll go on its merry way and fire up Windows. We'll come back to that in a minute. This is just telling it where bugs is. Actually, I come to think of it, I do it down here in a couple of ways here. This whole mess does it. It'll turn out that if you're working on a Windows machine with that USB drive, again, you don't need to change that, because in the next step down here, it'll figure out what the drive letter is for that USB drive, and it'll actually be using this line right here to set the path to WinBUGS. And the next part you can completely ignore unless you're using Macintosh or a Linux machine. Then it does things like it sets the work directory to the one where we're actually working here inside of our linear directory, and then I pull in some libraries. And I briefly mentioned R to WinBUGS and Coda. In addition, we'll be using the plotting package that's called Lattice in there, and then I go ahead and pull in those two scripts that have some function definitions, the bugstools.r and the beaglesbutilities.r in there. Then I go ahead and set a seed. Again, now that one it's not necessary. It's up to you whether to do it. The only reason I tend to do it is I may later on want to be able to replicate exactly what I've done, and because we're going to be doing things that use random number generators, namely the MCMC, as well as some of the ways that I set the initial estimates, I would actually get different results if I was to run this at a different time, unless I explicitly set the random number seed right here. Okay, let's see if we're come alive here. Okay, we can ignore that. I think we might actually be able to switch back over. We'll see. Okay, let's open it up and see. Seems to be talking to us. Okay. Let's actually see if Bugs opens okay. I never did actually show you the process of running a script file. So let me come back to the R in a minute. Now that we've got this actually appearing to function, let me pull in the script file again. Okay, and what I didn't show you is if you want, you can run this script file right from the GUI. In particular, if we open up over here under Model, the very last item in there says Script. So if the current window, if your currently active window is a script, you can go up to here, come down, and just simply select Script. And what you'll see, it opened up a window here, and of course again this particular model runs very quickly, so it's already done. So you can see it comes through. We're looking at the log file now that it creates. So the log file first of all shows the commands that you put in and any responses that result from it. So for example, when it did the check here, notice it responded with the statement model is syntactically correct right here. When we did the data statement, since it was correct, it said data loaded. So, after compile, it says model compiled, and so on. It's basically the same. In fact, it is the same response as you normally see at the bottom of the screen when you're running bugs interactively. So it goes through, brings in our initial estimates, generates initial estimates. We set the set monitors on a selected set of parameters and predictions. Did an update of 1,000. And when it finished that, it would have run this coda command, and what the coda command created, if we step over here to the directory that it's in, notice there are some files here. I'll just highlight them. The coda 1, 2, 3, and coda index, which contain the MCMC results in the coda 1, 2, and 3, and contains an index to where the different variables are located within those coda files. So that's there. Notice that following where it says stats here, so it says stats for A, it goes through and gives a set of statistics for the variable A, which was the intercept in our linear regression. Now, unfortunately, when I increase the size of the font here, things kind of run together in here, so it's difficult to tell where one number begins and the other ends, but I'm pretty sure here, for instance, it's giving me a mean of 5.725, standard deviation of 1.231, or MC error of 0.02944, and so on in here. So you can get the statistics, some statistics out about your posterior distributions. Down here it's plotted some marginal densities, you can see, in response to commands like density A. So now you've got a marginal density right here for our intercept. It does history plots. You can see the way the history plots are. Again, it's pretty much the same as you've seen before. Each color corresponds to a different chain, and for this example, things are nice fuzzy caterpillars. All the chains are well mixed, and all of them are pretty good horizontal fuzzy caterpillars here. Down here you have the autocorrelation plots, for example, and again for this one there's essentially zero autocorrelation going on for our slope and intercept, and just the tiniest bit of autocorrelation for our residual standard deviation. And then finally the save here saves the log file to a file called logodc. And if you look over here, you'll see a logodc file, which looks pretty much just like the screen we're looking at right now. Let's see, somebody's got a question here. Let's see, can I explain? Oh, deviance. Okay, we'll be talking more about deviance when I start talking about measures of quality of fit. So the question was, can I explain set deviance, which shows up well, actually, let's go back to the script here rather than looking at the results. So you can see here where I set deviance. Just quickly, the definition of deviance is minus 2 times the log of the likelihood. So it plays a function very similar to what you're probably used to with non-mem, where in the non-mem the objective function is well, I think it's minus 2 times the likelihood within an additive constant anyway. So it's essentially the same thing as that objective function. The difference here is with non-mem, what you see is it goes through this convergence process where finally it produces a single number, which would be the minus 2 times the well, it's minus 2 times the log of likelihood, again plus a constant, at the maximum likelihood estimates. In the case of a Bayesian analysis, deviance actually is an entire distribution. So it's going to be minus 2 times the log likelihood, but it's going to be spread out over the entire posterior distribution of all of the parameters and predictions in here. So hopefully that gives you a quick idea on that, and we'll spend a little more time when we start talking about things like model selection and so on. We'll spend more time on deviance and other quantities derived from deviance. Let's see, was there anything more I wanted to tell you about the script? Nothing that immediately comes to mind on the script itself. Let's go back to close that down for a moment. Let's go ahead and fire up R now from in here. Okay, and let's open up that linear 1b.r again. Okay, so we're back to that here, and I was kind of stepping through some of the pieces in here. So let's see, I think we were getting down to the part where we're going to be bringing in the data set here. Now in this case I've hard-coded the data set right in the R code. In the majority of cases we're not going to want to do that. We will have a data set sitting in a file someplace, and we will use various read statements in order to bring those data into R. But in this case I'm just going to do it very simply with just hard coding it. And notice this is actually identical to what was in that original linear 1.odc file, which makes sense because the data structure is for WinBUGS is practically the same as it is for R. It's a list of various objects where those objects are either scalars, vectors, or matrices. In this case it's just a list of two vectors. We've got a set of 10 values here for x and a set of 10 values for y that are going to match up to describe our data points that we're going to do the linear regression on. So we simply specify that. The name bugs data here plays no special role. It's simply the name I've given it in here. You could choose to call it something else. It's just that when you make use of it later you'll have to make use of whatever name you gave it. Then we need to specify initial estimates, and that's going to be a little bit trickier here. And now we're going to be dealing with some of the specifics of R to WinBUGS here, and R to WinBUGS will accept the initial estimates in a couple of different ways. I'm going to first show you what I think of as sort of the preferred way, especially if I'm going to want to run multiple chains but not necessarily know how many chains I'm going to run for every case. And what bugs will accept actually is that you can specify and I keep on saying bugs. Bugs is actually the name of a function inside the R to WinBUGS function, WinBUGS package. In fact, in a second here I'll show you a little bit more about that using the help file for R to WinBUGS. But let me just mention that it will accept initial estimates in a couple ways. One is to specify a function which, when every time it's called, it'll return a list of values that correspond to the initial estimates for one chain. The other approach is to give a list of lists. In other words, you would give a list containing a number of other lists, and there would be the number of lists would be the same as the number of chains you're going to do. That's more awkward because you have to pre-specify how many chains you're going to have, whereas if you use the approach of specifying it as a function, R to WinBUGS will simply call it however many times it needs depending on how many chains you tell it you want to run. So what I'm doing right here in this block here is using that approach of specifying the initial estimates as via a function. But now again, I still want to have different initial estimates for different chains, so I want to use some sort of a trick that will give me different initial estimates that are still useful but are different. The approach I'm using here is to use random number generation, where I specify the different components, the different initial estimates using random number generation, but I center those random numbers about what I think of as maybe being my best initial estimate, but then I want to spread around the values that I pass to it so that I can actually get a test of convergence. So let me point that so you can see that right in here. So here's the function. Bugs in it equals function. There's no arguments to the function. And then I specify the return value is going to be a list. And it should end up being a list in the same form as the initial estimates if I had hard-coded numbers once it actually gets called. And in this case, I'm going to specify my intercept A, my slope B, and my residual standard deviation sigma here are all going to be drawn from distributions. Well, now what I've done here, for instance, for the intercept is I'm going to use a normal distribution. I'm going to have it sample only one value with some mean, and I'll explain what this gibberish is here with the coefficient fit 1 and so on in a second. But that's just going to be the mean and then a standard deviation. Now you could choose to just hard code numbers in there that you think are suitable as initial estimates, both for here I would put a mean that I think of as my best initial estimate for the intercept, and then over here I would put some standard deviation on it that is that I think is a bit bigger than the standard error in this. Now what I've done here is before I actually called this, I did a little just a simple least squares linear regression before it. So what's going on here, this statement right here where I use the LM function, that just, an LM I think is just an acronym for linear model in R. So all I'm doing is a linear regression. So it's saying y, so I'm regressing y on x here. It's using the data that I've got right up here in BUGS data to do that linear regression. Fit will contain the results of that linear regression. And then what I've done here, for example, to get the standard errors for the regression coefficients, I run this statement happens to grab those, and then for sigma here I can grab that again. I have to run this summary of this fit object, and then I can pull off a sigma there. And then finally these statements down here, the COEF fit produces the regression coefficients, the point estimates from least squares linear regression, and the first one would be the intercept and the second one would be the slope in this instance. So I'm taking advantage of the linear regression there in order to get my initial estimates. Again, I could have chosen to hard code those instead. And then finally sigma here, you can see I've used a log normal distribution here because I'm generating a normal distribution for the log of sigma, and I happen to have put what amounts to a CV for sigma of equal to the sigma itself, so it's sort of like 100% CV on this thing. Is that right? No, actually that statement isn't quite right. But anyway, for the standard deviation I use the log of that and then take the exponential. But that's equivalent then to treating it as a log normally. Sigma is log normal. So I've generated initial estimates that way. So again, each time that gets called by R to WinBUGS, it'll generate a new set using random numbers generated using those values. So let's see, let's go list a question up here. Let's see. Let's see, Joe's giving me a message sounding bad. Okay. And it's like go to meeting locked up on me. Great. Okay, let's see. Everything's locked up. Okay, let's see. Okay. Okay, I don't know if I'm being heard here or not at the moment. I'm getting messages about sound problems. I just pulled the mic and put it back in. I don't know if that helped any. Okay. Okay, Joe, what are you catching? Anything there now? May have to reset the sound preferences. Okay. Hey Joe, you catching anything? No, I've got at least one says sounds good now. Let's see. I'm trying to make sure that the volume level is where it belongs here, because sometimes if I reconnect this thing it shoots it down. Yeah, it did. There we go. That should be a little louder there. Now that everybody's probably turned up their volume and I've just shouted their ears down. Okay. Yeah, Joe, you may actually want to ship me that other mic you were talking about and see if that makes a difference here, because it doesn't look like I'm going to get to Connecticut in a big hurry. Okay, where were we here? We were talking about bugs in it. I think we pretty well finished the story on that. The other thing we're going to need to tell R to WinBUGS is similar to what we did when we had to specify what parameters to monitor. We have to do the same thing. When we're working with R to WinBUGS, we want to tell it which things that we want to monitor. And because of some of the things that we're going to want to do here, I've broken that up into some pieces. And in particular, the first thing I do is I tell it what I've called here parameters to plot. These are going to be the parameters that I actually want to look at history plots for density plots, and to include in a tabular summary. And more often than not, I'm not going to be interested in looking at the predicted values in there. For this one, where we've only got 10 predicted values, it wouldn't be a big deal, but for most applications, you're going to have hundreds to thousands of data points, and you're not going to want to stare at history plots and a table that has all those quantities tabulated in. So this gives you the ability to take a subset of the things you're going to monitor and specify the ones that you want to create things like the history and density plots for. Then what I do is I have this other thing that I just called other RVs, in other words, other random variables that you still want to monitor and save, and you can specify those here. And in this case, that's going to be our predicted values, the y-pred values. And then the rest of this nonsense down here is just kind of the bookkeeping to pull it together. So I create this thing which is going to be all the parameters in here. The reason why I reset parameters to plot here is by default WinBUGS always monitors the deviance, so you don't actually need to specify it, tell it to save it. But here I wanted to include it in the list of parameters to plot that I'll work with after WinBUGS actually runs. Okay, and finally we get down to sort of the business end of this, which is actually going to be to run the WinBUGS. Most of that's going to be going on right here, where first of all I specify how many chains I'm going to want, how many iterations per chain, how many burn-in per chain, and then a thinning parameter. And so the first three are probably obvious: the number of chains you want, the number of iterations per chain, and how many of those iterations are you going to treat as burn-in and essentially throw away. The end thin, this thinning parameter, it tells you, excuse me, is telling bugs how many of those iterations do you actually want to keep results from. And so when it's 1, it's going to keep all the iteration results. If I was to set it to say something like 5, that would mean that I would only keep every 5th iteration result for subsequent analyses. Now the only reason you would probably do that is just simply because of storage space, both within RAM, because it's going to be sitting in RAM while it's running, as well as your hard drive afterwards. Also, actually, one of the more limiting things you may find is R is the most likely bottleneck when it comes to the size of data objects in here. So you may end up cutting back a bit because of that. Also, if you've got MCMC results that have a lot of autocorrelation in it, you don't lose much by thinning. You don't really gain anything except efficiency and space utilization, but again, you won't lose much by thinning out if there's already a lot of autocorrelation in there. Let me show you a little bit more about bugs here. Let's see. Let's fire up our help file so we can actually see some of the elements here. So let me do help start here to fire up the help files for various R things. Okay, let's go to packages. And let's take a look at R to WinBUGS. Here we go, right there. Okay, so there is a whole slew of stuff in here. It's not too many humongous things, but there's a number of things in R to WinBUGS in here. But the thing that you're most often going to be using that comes within this is this one function called bugs. Let's go ahead and fire that help file up. Let me make it maybe just a tad bigger here. I don't think it got bigger. Come on, get bigger. Oh, because I was pushing the wrong button, that's why. There we go. Okay, so this is the function that we're actually using. So for instance, if we step back to where we were, you can see here's where I'm making a call to that bugs function. So let's see some of the pieces of that you may want to manipulate, because notice it's got this rather large argument list going on in here, and frankly there's only a few of those that you're likely to want to manipulate. Most of the time you can treat the bulk of this as kind of boilerplate that you would use over and over again, but it's worth giving you a quick overview of of what's in here. So again, you get this whole slew of arguments in here, but let me point you to a few of them here. So one that you'll always be using is going to be for the data. So and generally you're going to be passing an R list that basically has the same format as you would for even doing a WinBUGS from the GUI. We talked about the formats for the initial estimates, and if you look at this, you'll see additional discussion about that aspect here. There's the parameters to save, so that's which is equivalent to which ones that you're going to want to monitor, so we're going to want that. Then you need to specify your model file, and as you can see, it says the extensions here have to either be .bug or .txt. The convention I'm going to use throughout the course is I'm going to use the .txt extension. I find that's probably the more convenient one for me to keep in mind, but you can take a look at this and see what you think your preference might be. You can always change it to that. But for now, I will be using the .txt extension for the work we're going to be doing. That also it also requires that the model file, as sort of implied by that .txt, be just an ASCII text file. So, for instance, if you wrote up the original BUGS model using the WinBUGS GUI, by default it saves what it calls its .odc files, which is not an ASCII file. So if you're going to save a file from WinBUGS that you've created there, you would use when you do the save or do a save as, you can specify that you want to save it as a text file. So you'd want to do that. Let's see, then you're going to specify number of chains, number of iterations, and the number of burn-ins. So in the n-iter and n-burn-in are both the numbers per chain. We talked about the n.thin, same deal there. Actually, I've never used nsims. I just noticed that one there. I think I'll ignore it for now. Let's ignore the ones I never use for the moment here, which is nsims and bin. Debug is one that you do change sometimes. The default for debug is false, and all debug does, by the way, if debug is false, what will happen, as you'll see when we run this, is R2WinBUGS will launch a WinBUGS session. You'll actually see the GUI interface open up. And if debug is false, when it gets to the end, it'll close out WinBUGS. So it'll stop and it'll just return control to R. If debug equals true, what it'll do instead is WinBUGS will stay open. The GUI will remain open, and that is useful if you want to do some debugging, because if it hits an error, then you'd be able to see what the error message is within WinBUGS, and perhaps do additional interactions with WinBUGS at that point, after all the various things have been entered in by R2WinBUGS. So often when I'm doing my initial work and building up a model in the data set and so on, as often I'll set debug to true in order to deal with that. Let's see, we'll skip DIC for now here. Let's see, I know there was another one I wanted here. Oh yeah, there's various things you can take a look at that may be of interest here and there. Let's see, bugs directory can be important, particularly if your bugs is not in the default directory, because then you would actually want to specify it. Program we don't need to worry about here because we're always going to be using WinBUGS for the moment. Here's one that's I do also change, clear working directory. So when R2WinBUGS works, it's actually going to generate a number of files, things like data file, initial estimates files, and these coda files, for example. If clearwd equals true, it will delete those files when the run is over. which most of the time you're perfectly happy with. But again, if you're kind of in an early sort of development mode, in sort of a debugging mode, you might want to set clear WD to false, so it actually saves them there, and that allows you again to use those files yourself to sort of deal with the debugging and such. Let's see, is there anything else I want to tell you about? No, I think for now I would leave the I'll leave the rest of the options here, but you can go, you know, obviously I would recommend that you dig in here, look at the help file here, since this is a tool that you're going to be using over and over again as we go through this. Okay, let me hide that away and come back to this. So let's see how we used it. So we've got, notice here for the data argument here, we use that bugs data object we created. For inits, that's where that bugs init function we created gets passed. For parameters to save, it's the parameters object that we generated up at the top here. The model file right here. Notice here, this is where I take advantage of the bit of using the that model name I specified on top. So this is assuming that the name of your model file is the same name that we specified up on top, which happened to be linear1b, and then it's going to have a .txt. So it's assuming it's called linear1b.txt, which is exactly the name of the file in our working directory here. And then the rest of this nonsense is just tacking on the full path to that particular file here. So in here I'm specifying number of chains, number of iterations, number of burn-ins, thinning, and so on. And I've got the defaults here where I've got clear working directory true and debug equals false. In here, specify my bugs directory, which was defined up near the top of this file. And the working directory is just going to be the current working directory, which you can get using the getwd command. The rest of the nonsense is actually, so if you want to run this on something like the Macintosh, which I do, that'll take care of that. But it's got some logicals in there such that if you're working with Windows, it'll essentially ignore these. So most of the time, you're actually going to be leaving this alone. You'll change things like the number of chains, the number of iterations, and so on. But this part that I've highlighted here will usually be sort of boilerplate. The main exceptions to that will be when you come in and change the clear working directory here and debug in order to deal with some debugging when you encounter errors and you want to be able to dig deeper to find out where those errors are. Let's see. Actually, you know what? Let me actually run this so that you can see the results, and I can tie the results back to some of the rest of the content of this file. So to run this, well, we can do it a couple of ways, but the way I'll do it here is I'll just select the entire file and go up here and hit the run liner selection up here. And run it. If everything's okay, almost everything on our left will be red. Okay, notice it fires up a WinBUGS window. WinBUGS runs. Again, this is a real quick model, so it's already finished, and come back and return control to R. Few plotting things. Okay, it's actually come to the end here. Actually, let me point up a couple of things. Most of this is going to be boring. The errors that you see right here are ignorable ones. It's basically saying it can't remove files, the files that's listed here, and the reason it can't remove them is because the bugs function already removed them, so you can ignore this. So let's take a look at some of the things that it just did and then come back and show you how it did them. So if I come back to my directory here, one thing that may or may not be evident is there's a new folder here called Linear 1B. And we go down inside there. And there's a number of objects in here. First of all, the model shows up. That model file is there, as well as the R script. So something in here has gone through and saved copies of those to serve as a record for what you had done. There's this thing called linear1b.fit.r save. That's actually a file containing all of the MCMC iterations in the form of an R object. The linear1b.summary.csv is a summary table. And then we have a bunch of PDF files, which are a bunch of plots. Let me actually go up to back into up here, and let's see, do I have the right thing open? Well, not quite. Let me open this up. Okay, what I'm doing is just going into the Mac side of the house here, where I can look at some of these things a little more easily. Actually, let me okay, so I'm back inside the same place we were. Let me open up the Linear 1B directory. Let me open this up in Excel. This is the summary table that it generates, so you can see what you get out of that. Okay, let me make that a little bigger. Okay, so this is a summary table that you get that it reports out. Notice the things it saves here are prints out, or the rows here correspond to the deviance quantity. Again, that's our -2 times the log likelihood, our intercept A, our slope B, and our residual standard deviation sigma. It reports the mean for our MCMC samples, standard deviation of them, something it terms the naive standard error, which is nothing more than taking the standard error here, our standard deviation, and dividing it by the square root of the number of iterations. So if we think back, actually, how many iterations did we do? We did, okay, let's see, we did 3 times 1,000, but we actually threw out, so there, the first 100, so we had 900 that we kept, and times 3, so 2,700. So the naive standard error, assuming I said things correctly, should be this standard. So right here, if I took 3.26 and divided it by the square root of 2,700, I should get this number, assuming I did that right. And then the number here, the time series standard error, attempts to adjust for the fact that there's some autocorrelation in the MCMC samples. So the true standard error of the posterior mean in here wouldn't be the naive standard error, it would be something more like the time series standard error. So again, these are standard errors for the posterior mean that it's referring to. And if you look through these in general, you'll see the time series standard errors are a little bit bigger. For whatever reason, that's actually not true with B, but usually, actually it's not true for A either, which is kind of curious. But then there's an approximation involved in that autocorrelation adjustment, so that probably has something to do with it. Then it gives a few quantiles here, as you can see. Gives you the 2.5 and 90 to 7.5 percentiles. So that then would be a 95% credible interval for the corresponding parameters. And then you get the quartiles here, 25, 50, and 75%. So we've got our median as another measure of central tendency. Then finally, the last thing here is something that it terms effective N. This would be the number of independent random samples number of independent random samples that contain the same amount of information as the MCMC samples that we did. So in general, usually effective n will be somewhat smaller than the number of MCMC iterations that we did. Again, this is adjusting for the autocorrelation. The more the autocorrelation, the smaller the effective n would be. And then finally, the other thing that we get out of this is we get a few plots. Let me show you those. Much the same sort of plots, or at least some of them are much the same as what we saw when we were working with the WinBUGs directly. They're a bit nicer when they come out of R in here. So for instance, here we have our history plots for our intercept, slope, deviance, and our standard deviation here. Again, we've got fairly decent fuzzy caterpillars here. If you wanted them even nicer and fuzzier, you could probably do maybe 10,000 samples instead of 1,000, but they're generally looking pretty good. Here's the some density plots using the density plot function within R to generate these, and again, you can see those, so you can, you get a quick look at what the estimated values then of these quantities are. So for example, if we look at our intercept, you can see that's centered, it's a bit above 5, somewhere 6-ish or so, and then you've got you can see it's spread roughly from around 3-ish up to right around 8-ish or so there. So you can get some idea of the posterior distribution of the parameters that way. Oh, push the wrong buttons, all right. Apparently I pushed another wrong button. Let me do that again. There we go. Okay, this one we'll talk a bit more probably for next week's session. This is the so-called Gelman-Rubin-Brooks plots, or Gelman-Brooks-Rubin plots, or one of those, some combination of GB and R. This is a convergence diagnostic. Frankly, I've never thought it told me a whole lot more than looking at the history plots, but it's another way of seeing it. Just give you a quick idea, it's essentially a measure of the ratio of the, and I got to keep this straight, of the inter-chain variance divided by the within-chain variance, between chain versus within. So it will generally be greater than or equal to 1. And then the better the convergence is, the closer it will be to 1. And if I was looking for a quick rule of thumb, you're looking for this to have fallen, at least towards the end here, to something, on the order of, less than 1.05 anyway. Again, for this particular problem, we're easily within that rule of thumb. And then finally, we just get a fairly simple picture of a fit. So this is this is looking at our posterior predictions overlaid on our observed data. Observed data, just the black dots. We've got a posterior median running through it in blue, and then the red dotted lines here correspond. Let's see, in this case, I believe I did the 5th and the 95th percentiles, so that would represent a point-wise 90% credible interval for the predicted values here. And so we can see we've generally captured the broad shape anyway of the data here. So those were all produced by that R script. So let's go back to that and sort of point up where some of these pieces come from. So we ran the BUGS script. That creates an object here called BUGSFit, which is quite a complicated critter. I probably recommend you take a look at the documentation to get an idea of what that object consists of, but it's got several components. within it. It actually reports back the MCMC iterations in a couple of different formats, as well as a few other derived parameters. We're actually, at least for this example, I'm only going to be using one of those formats in here for doing the subsequent work. So it's going to return that. In fact, if we were to look at, if you do, for instance, the str command that gives you a sort of summary of the attributes of an object here, you'll see that it's got, it's complicated. So you can see, for example, it's a list of 24 different R objects in here. It reports back things like the number of chains, the number of iterations, and so on. It reports back this thing called a sims.array, which is an array, which is actually the object we're mainly going to be working with, which in this case has a number of, the first dimension corresponds to all the different iterations, so that's, you can think of that as the rows. Then we've got the next dimension has to do with the number of chains, so that's going to go from 1 to 3 in this case, and then 1 to 14 corresponds to all the different quantities we've saved. The way I tend to prefer to think of this Sims array object is each chain produces a matrix, where the rows correspond to the iterations and the columns correspond to the different quantities that we've saved. And then you have one such matrix for every chain. So think of this as like a, as a stack of matrices then. And in this case, it's a stack of 3 matrices. And that's what we'll work with. We'll either take that or we'll go ahead and stack those 3 matrices on top of each other just to create one big matrix containing all the iterations. But you can see there's a bunch of other objects all buried in here that you can look at, including some summary statistics within there. Okay, so that's that object. One of the first steps I generally do in these is I go ahead and save. What's called save.model here, that creates a directory to save stuff in. So when let me go back to the directory here. So recall it created this linear1b.subdirectory. It's also the same thing that writes things like the model file and the R script to that directory. But more importantly, let me go back there. It writes out this thing here, the linear1b.fit.rsave, which contains that BUGSFit object. And the reason I do that is often it's a big thing. For complicated models, it's a very expensive thing to produce computationally in terms of the time spent. So it's a good idea to save it in case you want to recover it later on to do any additional plots or statistics on it. So you generally would, okay, I just pushed another button I didn't want. Let's see. So it would be a good idea to save that so that later on, if you need to do something you didn't foresee that you would want, you can just load it back up without rerunning the entire MCMC script. And if you do need to load it, there's a line here which is commented out, but if you uncomment that, that would read that object back in so that you could work with it later on. So that takes care of that. The rest of this is just pulling together. All this is doing is taking that BUGSFit $Sims array and assigning it the name Sims array. That's probably not good form from the standpoint of memory usage, but it just simplifies the coding downstream. And then all the posterior is here is nothing more than taking that Sims array, which has those 3 matrices in this case, and stacks those 3 matrices one on top of the other to create one big matrix. And that's actually what we'll use for most of the statistics we'll do, is the thing that we call posterior here. And then the rest of it is, now that we got it, let's make some of the plots and tables and so on. First step in here is to create a PDF file. And if you prefer a different graphics format, I'll leave that to you. There's formats like PNG and I think JPEG and a few others. So if you prefer to save your graphics in a different format, you can do that. But I'll use the PDF here. So the PDF graphics device is specified that way, and then I specify the file name. The format I use here is one, so this is, first of all, it's writing it into that linear 1B subdirectory we created above. This format where I say a name and then stick on the end of it %03D and use the argument one file equals false, that will create one file per plot, which I usually find easier later on if I want to bring those into documents. In here, if you prefer just to have one big file that has multiple pages, you can make this one file equals true. This thing is doing nothing more than subsetting the Sims array and only grabbing those things that above I said I wanted to plot. So if you recall above that we had specified this parameters to plot, which was a subset of everything that we're going to do. In this case, it's just A, B, and sigma. So this is going to be a subset of that Sims array containing only A, B, and sigma, and I think deviance too in this case. And that gets passed to this function called, that we're calling right here, that's called parameter plot table. That's one of those handy dandy functions inside of inside the BUGSTools.R function, and it's actually worth taking a quick look at that. Let me pull that in. Go into BUGSTools, BUGSTools.R. So there's a bunch of stuff in here. Won't go through all of it, but some of these things, like here, this MC history function here takes that Sims array object, reorganizes it a bit, and then creates a plot. So those history plots we were looking at are actually created by this MC history function right here, which is subsequently called by that parameter plot table function. Then the density plots you saw were created by this MC density function. Again, feel free to take a look at that, and you can see how those were generated in here. If you want to learn about things like the density function and how you can use that in conjunction with the lattice plots right here to generate density plots like the ones that were shown. Well, that save model function, which is where we save the bugs fit quantity and so on, that's right here. So it's mainly moving around a bunch of files, and the key step is right here where it does that saving that bugs fit object. And so in fact the only two functions in here that I usually call directly are going to be save model and parameter plot table. Oops. And here's your parameter plot table function where it's defined here. And you can see again you put in that, I called it parameter array, but that would be that Sims array object here that you're passing in. Notice it calls MC history and then MC density in here. It creates those Gelman-Rubin-Brooks plots right here. And then finally the rest of this mess here is creating that summary table within. So anyway, if you're curious, you can obviously dig around, but that's just telling you a little bit about the nuts and bolts that are going on here. So that creates that. Now when it creates that table in parameter plot table, it just returns it as an R object initially. In fact, we can even, when you run this, you don't necessarily have to go open the file. If I just type ptable right here, you'll see it actually gives you an iteration of that table as an R object, because it's just a data frame within R, so you can actually see it right there. And then the next statement right here, the write CSV, is then writing that out, just writing that out to a file. Again, it's inside that linear 1B folder. And then finally we come to the plots where we do our posterior predictions in here. Now, in fact, let me just comment. The stuff pretty much, sorry, moving too fast. The stuff going roughly from, actually let's go from about here. Sorry for my bad mouse usage there. Okay, from about there all the way down to about there is kind of boilerplate throughout the course. Rarely will we change those elements other than where before I mentioned sometimes we'll set debug equals to true, for example. But for the most part, this part of the code will be boilerplate and we'll use the same code over and over again. Where things tend to change is going to be down here where we're going to want to start looking at things like posterior predictive distributions and other model fitting diagnostics, and those things tend to be more model specific and thus will change from case to case. So let me just show you the one we've got for our linear example. The first statement here is, okay, where'd my mouse go? There it is. Right here is subsetting the posterior object. Recall again, the posterior object is actually let's show you what the posterior object, let's just look at the first few rows of that. Okay, so here's the first few rows kind of folded over here. So you can see that you've got a bunch of rows. In this case, it's just showing you the first 6 rows, which correspond to the first 6 MCMC iterations. And the columns correspond to the different quantities that we've monitored. So you've got your intercept, slope, standard deviation, all the predictions here going, and again, there were 10 values, so we've got 10 predictions, and the deviance values here. So that's the kind of object we're working with right here. And all I'm doing with this statement right here is grabbing the subset of that posterior which contains all of my predicted values, the things that begin with ypred. So that's taking this object and just grabbing, you know, all these ypred columns and saving only those and discarding the rest, and save them in an object called pred. Then the next statement I hear is I take my data set here, my bugs data $x and bugs data $y, so that's my x and y data values, create a little data frame for those. I then create a type variable, another column in there that I call type, and it's going to be observed for my observed data. And then I'm going to do some statistics that I want to plot. Like, recall in the plot we had a posterior median and a 5th and a 95th percentile in there. So I'm going to create an object with those, and what I'm doing here is creating a data frame which is identical to my original data, but I'm going to stack them 3 high because I'm going to include all 3 of the statistics in there. And then this step right here is generating those quantiles, the 5th, 50th, and 95th percentiles in here in this statement, and stringing them out as a vector and creating that as a new column inside this object x1. Actually, what I'm doing is I'm replacing the data within that with the predicted values in here. I create, again, I replace the type variable here with the names, 5 percentile, median, and 95 percentile. So again, that's generating those statistics and doing some bookkeeping on them. And then finally, I just stack the observed data and predicted data all together. So it's observed data in the stats within the same data frame, and that's all going to, and that's what I'm going to be plotting with. I'm going to use the lattice graphic item here, XY plot. To do that, I'm going to be plotting y against x, The data is all going to come out of that x1 object. I'm going to want to use different symbols for each type. Recall the type was either observed, 5 percentile, median, and 95 percentile. And I want each one of those to be formatted a little different, but I want them all to be on the same panel. And that's what the groups is doing, is it's plotting everything on the same panel, but it's allowing me to format each one of those items a bit differently. And that's what I'm doing here. So for example, this is saying format the first ones as line plots and the last one as just symbols. And that's what the L and the P are referring to. By the way, by default, it's going to order them alphabetically. So, and actually the numbers will come first. So the 5th percentile and 95th percentile will be the first two, then median, then observed, and that's why this order. So I'm using the L format for the statistics and the P for the data. LTY 3s is the line type. 3s are dotted lines. 1 is a straight line, and 0 is no line in there, which is exactly what I want. Again, for my this is for my 90% credible interval, for my median, and for my data. And then colors, actually I should go to more modern practice. This is an old piece of code I wrote. 2 happens to be red, 4 is blue, and 1 is black. I could have actually used character strings there and just said red, red, blue, black, and that would have worked too. PCH is the symbol to use. I don't want symbols for the first 3. I only want them for the observed data, and 19 is just a filled circle. The rest of it is just little formatting things. Some of them having to do with like size of the symbols, and I'm just telling it I want to use X for my X label and Y for my Y label. Actually, it would have done those by default. And all of that is just leading to that thing we saw before. Let me go up to that. Excuse me, it's being slow again. Here it goes. Okay, let me remind you what that thing looked like. Oops. There we go. Okay, so and that's, again, that was what produced this plot right here. To create that. We'll see when we go on and start fitting like multiple individuals in that, how we can set this up to do essentially a plot like that for each individual later on, using essentially the same format that we have there, with fairly minor changes on it. So that's part of the, I've made it maybe overly complicated for the case here where we've only got a single panel to show, but we'll find that it rather easily extends when we get to things where we want to look at multiple individuals later on. Okay, let me take a quick breath there, and what we're going to do, let me find what I did with my slides. Let's see, there we go. Okay, I think I've done pretty much all the demo things that I wanted to do, and we're coming up towards the end of our time anyway. Let's see. Yeah, let me take you to your homework assignment. So what I want you to do for Thursday, and this is what we'll go over during our Thursday lab session, is to start working with these R tools for WinBUGS. Probably the first step I'd recommend is to go ahead and just run that linear case that we just did to make sure that you can get it to run on your machine and so on. But then what I'd like you to do is go back to our first hands-on example that we did last week, where we did that all using the GUI, and now convert that to a setup where you're going to use an R script for running it. Recommendation here is to use the linear1b.r script that we were just working with here as your template. For now, again, let's just go ahead and hard code the data in the R script, and we'll cover reading from files in a subsequent example. So in other words, do it pretty much the same way we just did within the linear case here. You might want to simply keep your initial estimate approach here a little simpler than the one I did. In the linear 1B case, I used the linear regression to generate initial estimates. I recommend you might make it easier on yourself and just sort of hard code the means and the standard deviations that you use to simulate the initial estimates from. And then I'm recommending you do 3 chains by 1,000 iterations with 5,000 iterations, burn-in iterations per chain, and thin by 5. Go ahead and then produce diagnostic plots and a summary table using the parameter plot table function, again, just like we did in the linear 1B example, and plot the posterior predictions overlaid on data. So the main change that you're going to be working with here is really just that you're going to be using that nonlinear model, that Emacs model that we had used for the example 1. So for the most part, it should be a fairly straight ahead modification then of the linear 1B template in order to do it. So that's what I'm going to do. The task I'm going to set you then for Friday. Let's see, any last questions or comments before I close out? See, I haven't seen anything pop up yet here anyway. Certainly, again, you can feel free to ask any questions via the course, our course website here, so we can always follow up on that if you don't have anything immediate now. So I guess I will go ahead and close out and look forward to talking to you again on, I keep getting my days mixed up, on Thursday, okay? Again, somewhere between now and then, I will see what I can do about recording lectures for next week. And talk to you then.